In the mathematical field of numerical analysis, a Newton polynomial, named after its inventor Isaac Newton, is the interpolation polynomial for a given set of data points in the Newton form. The Newton polynomial is sometimes called Newton's divided differences interpolation polynomial because the coefficients of the polynomial are calculated using divided differences. For any given finite set of data points, there is only one polynomial, of least possible degree, that passes through all of them. Thus, it is more appropriate to speak of the Newton form of the interpolation polynomial, rather than of the Newton interpolation polynomial. Like the Lagrange form, it is merely another way to write the same polynomial. Definition: given a set of k plus 1 data points where no two xj are the same, the interpolation polynomial in the Newton form is a linear combination of Newton basis polynomials with the Newton basis polynomials defined as for j greater than 0 and the coefficients are defined as where is the notation for divided differences. Thus the Newton polynomial can be written as the Newton polynomial above can be expressed in a simplified form when or arranged consecutively with equal space. Introducing the notation for each and the difference can be written as, so the Newton polynomial above becomes, is called the Newton forward divided difference formula. If the nodes are reordered as, the Newton polynomial becomes, if are equally spaced with x equals and for I equals 0, 1, k, then, is called the Newton backward divided difference formula. Significance: Newton's formula is of interest because it is the straightforward and natural differences version of Taylor's polynomial. Taylor's polynomial tells where a function will go, based on its y value, and its derivatives at one particular x value. Newton's formula is Taylor's polynomial, based on finite differences instead of instantaneous rates of change. Addition of new points. As with other difference formulas, the degree of a Newton's interpolating polynomial can be increased by adding more terms and points without discarding existing ones. Newton's form has the simplicity that the new points are always added at one end. Newton's forward formula can add new points to the right, and Newton's backwards formula can add new points to the left. The accuracy of polynomial interpolation depends on how close the interpolated point is to the middle of the x values of the set of points used. Obviously, as new points are added at one end, that middle becomes farther and farther from the first data point. Therefore, if it isn't known how many points will be needed for the desired accuracy, the middle of the x values might be far from where the interpolation is done. Gauss, Stirling, and Bessel all developed formulae to remedy that problem. Gauss's formula alternately adds new points at the left and right ends, thereby keeping the set of points centered near the same place. When so doing, it uses terms from Newton's formula, with data points and x values renamed in keeping with one's choice of what data point is designated as the x0 data point. Stirling's formula remains centered about a particular data point, for use when the evaluated point is nearer to a data point than to a middle of two data points. Bessel's formula remains centered about a particular middle between two data points, for use when the evaluated point is nearer to a middle than to a data point. Bessel and Stirling achieved that by sometimes using the average of two differences, and sometimes using the average of two products of binomials in X, where Newton's or Gauss's would use just one difference or product. Stirling's uses an average difference in odd degree terms, Bessel's uses an average difference in even degree terms. Strengths and weaknesses of various formulae. Gauss versus Bessel and Stirling. Bessel and Stirling require a bit more work than Gauss does. The desirability of using Bessel or Stirling depends on whether or not their small improvement in accuracy over Gauss is needed. Bessel versus Stirling. The choice between Bessel and Stirling depends on whether the interpolated point is closer to a data point, or closer to a middle between two data points. But it should be pointed out that a polynomial interpolation's error approaches zero, as the interpolation point approaches a data point. Therefore, Stirling's formula brings its accuracy improvement where it's least needed. And Bessel brings its accuracy improvement where it's most needed. So, Bessel's formula could be said to be the most consistently accurate difference formula, and, in general, the most consistently accurate of the familiar polynomial interpolation formulas. Divided difference methods versus Lagrange. Lagrange is sometimes said to require less work, and is sometimes recommended for problems in which it's known, in advance, from previous experience, how many terms are needed for sufficient accuracy. The divided difference method have the advantage that more data points can be added, for improved accuracy, without redoing the whole problem. The terms based on the previous data points can continue to be used. With the ordinary Lagrange formula, to do the problem with more data points would require redoing the whole problem. There is a barocentric version of Lagrange that avoids the need to redo the entire calculation when adding a new data point, but it requires that the values of each term be recorded. But the ability of Gauss, Bessel and Stirling to keep the data points centered close to the interpolated point gives them an advantage over Lagrange, when it isn't known, in advance, how many data points will be needed. Additionally, suppose that one wants to find out if, for some particular type of problem, linear interpolation is sufficiently accurate. That can be determined by evaluating the quadratic term of a divided difference formula. If the quadratic term is negligible, meaning that the linear term is sufficiently accurate without adding the quadratic term, then linear interpolation is sufficiently accurate. Of course, only a divided difference method can be used for such a determination. For that purpose, the divided difference formula and or its x0 point should be chosen so that the formula will use, for its linear term, the two data points between which the linear interpolation of interest would be done. The divided difference formulas are more versatile, useful in more kinds of problems. The Lagrange formula is at its best when all the interpolation will be done at one x value, with only the data points y values varying from one problem to another, and when it's known, from past experience, how many terms are needed for sufficient accuracy. With the Newton form of the interpolating polynomial, a compact and effective algorithm exists for combining the terms to find the coefficients of the polynomial. Accuracy when, with Stirling's or Bessel's, the last term used includes the average of two differences. Then one more point is being used than Newton's or other polynomial interpolations would use for the same polynomial degree. So, in that instance, Stirling's or Bessel's is not putting an n-1 degree polynomial through n points, but is, instead, trading equivalence with Newton's for better centering and accuracy, giving those methods sometimes potentially greater accuracy for a given polynomial degree than other polynomial interpolations. General case. For the special case of xi equals I, there is a closely related set of polynomials, also called the Newton polynomials, that are simply the binomial coefficients for general argument. That is, one also has the Newton polynomials given by in this form. The Newton polynomials generate the Newton series. These are in turn a special case of the general difference polynomials, which allow the representation of analytic functions through generalized difference equations. Main idea: solving an interpolation problem leads to a problem in linear algebra where we have to solve a system of linear equations. Using a standard monomial basis for our interpolation polynomial, we get the very complicated Van de Monde matrix. By choosing another basis, the Newton basis, we get a system of linear equations with a much simpler lower triangular matrix which can be solved faster. For k+1 data points, we construct the Newton basis as using these polynomials as a basis for we have to solve the polynomial interpolation problem. This system of equations can be solved iteratively by solving Taylor polynomial. The limit of the Newton polynomial if all nodes coincide is a Taylor polynomial, because the divided differences become derivatives. Application. As can be seen from the definition of the divisor differences, new data points can be added to the data set to create a new interpolation polynomial, without recalculating the old coefficients. And when a data point changes, we usually do not have to recalculate all coefficients. Furthermore, if the shear distributed equidistantly, the calculation of the divided differences becomes significantly easier. Therefore, the divided difference formulas are usually preferred over the Lagrange form for practical purposes. Example: the divided differences can be written in the form of a table. For example, for a function f is to be interpolated on points, right, then the interpolating polynomial is formed as above, using the topmost entries in each column as coefficients. For example, suppose we are to construct the interpolating polynomial to f equals tan using divided differences at the points using 6 digits of accuracy. We construct the table thus: the interpolating polynomial is given more digits of accuracy in the table. The first and third coefficients will be found to be 0.